The danger arises when an engineer selects a material based solely on a single published tensile strength value. A datasheet might boast a high breaking point, but if you ignore the environmental and physical stresses of the actual application, that gear strips and shatters under load. A published datasheet number is meaningless until you understand the rigid, highly standardized conditions under which it was generated in the laboratory. To give these numbers any comparative value, the plastics industry relies on ASTM D638. This is the mandatory global standard required to test the tensile properties of rigid and semi-rigid engineering plastics. Polymeric materials are highly sensitive to their environment. Even slight variations in ambient temperature or moisture will skew the test results and render the data invalid. Because of this, pre-test conditioning is strictly enforced. Under ASTM D618 Procedure A, specimens must be held at exactly 23 degrees Celsius, give or take 2 degrees, and at 50% relative humidity prior to testing. The published tensile value you see on a spec sheet is a controlled laboratory artifact. To extract real utility from it, we have to look closely at exactly how the test is physically conducted. Laboratory tensile testing requires a specific specimen geometry. Simply clamping down on a rectangular block of plastic will not yield accurate results. The grips themselves can crush the material and cause premature failure. This schematic shows the ASTM D638 dog bone specimen. It requires a 165 mm length, 50 mm gauge length, and 3.2 mm thickness. This forces stress into the narrow 13 mm center, ensuring the material fails there rather than at the wider 19 mm grip ends. This diagram details the Universal Testing Machine, or UTM. The dog bone specimen is mounted vertically between two holding grips, one anchored to a stationary base and the other attached to a moving crosshead equipped with a load cell. To initiate the test, the grips are tightened evenly to prevent slippage. The drive mechanism then pulls the moving crosshead upward at a constant specified velocity. For flexible and semi-rigid materials, this speed is typically 5 mm per minute. This precise combination of specimen geometry and controlled mechanical pulling cleanly isolates the internal resistance of the polymer as it deforms. As the machine pulls, an extensometer is used to measure the strain. This is the exact ratio of the specimen's change in length relative to its original length. While traditional extensometers clip physically onto the plastic, modern testing frequently utilizes non-contact optical systems, as seen in this image. These use video and laser devices to track target marks on the specimen, solving alignment and weight issues associated with highly elastic or fragile materials. Simultaneously, the load cell at the top of the machine detects the increasing physical resistance generated by the specimen. This resistance is recorded as force. This graph plots those two continuous data streams against each other to create the stress-strain curve. It tracks the initial resistance upward to the yield point, where the material permanently deforms without an increase in stress, and continues until the final rupture at the break point. The entire shape of this curve provides the true engineering footprint of a material's mechanical capability. The final breaking number is only a single data point at the very end of the line. This data readout presents a practical scenario. We need to determine the exact load required to reach the yield point for a custom specimen. We know our specimen width is 8 mm, its thickness is 3 mm, and the material's established yield strength is 600 kg per square centimeters. First, we convert the physical dimensions from millimeters to centimeters to match our strength unit. That gives us a width of 0.8 centimeters and a thickness of 0.3 centimeters. Multiplying these together gives our specimen a cross-sectional area of 0.24 square centimeters. The core formula states that tensile strength equals applied load divided by area. By rearranging to solve for load, we multiply yield strength by the area. 600 kilograms per square centimeter multiplied by 0.24 square centimeters equals exactly 144 kilograms of force. This calculation proves exactly how physical dimensions of a manufactured part scale directly to the sheer mechanical force recorded by the testing machine's load cell. The math works perfectly, but only within the rigid ASTM sandbox. Introduce real-world variables, and these baseline numbers immediately distort. The first major variable is strain rate. If you increase the speed of the crosshead during testing, you force the material to behave differently than it did at the standard 5 mm per minute. This animated curve demonstrates that higher strain rates increase both the tensile strength and the modulus of the material. It shifts the curve steeply upward, but it comes at a cost. The elongation is inversely proportional. The material becomes stiffer, but loses its ductility. The second, and often more aggressive variable, is ambient temperature. This second animation illustrates what happens when heat is applied. Elevated temperatures drastically lower the tensile strength and modulus, dropping the curve downward. However, the elongation increases significantly, pulling the curve out along the horizontal axis as the polymer softens. Relying on room temperature, standard speed datasheet values to design a component intended for a high heat or high impact environment is a guaranteed path to mechanical failure. Beyond environmental factors, there is a hidden variable baked into the physical part itself: molecular orientation. The manufacturing process literally dictates internal strength. During injection molding, polymer chains and glass fibers align themselves based on the directional flow of molten plastic as it enters from the gate. A gate located at the top end of a part forces a parallel alignment down its entire length. If you pull this part from end to end, it will yield the highest possible tensile strength. Move the gate to the side and the physics change. The material flows in, crashes into opposing walls, settling into a tangled, chaotic molecular orientation. This random dispersion of fibers drastically lowers the material's ability to resist longitudinal pulling forces. It is structurally weaker, despite being molded from the exact same batch of plastic. A single tensile strength number on a supplier's datasheet cannot account for your strain rate, your operating temperature, or your specific mold design. True engineering requires abandoning the datasheet illusion. You have to utilize the full stress-strain curve and actively calculate for the physical realities of the final application.